Now that we know what a hypothesis test is, let's consider some examples. This example continues the battery runtime example. We just want to plug in the data to see whether we do reject or not reject the null hypothesis. So in this battery runtime example, if you remember, the null hypothesis is mu equals 500, and the alternative is that mu is less than 500. And we observed a random sample of size 45, in which the sample mean is 455. And the standard deviation is 42. Suppose that we choose a significance level, because to do hypothesis test, we need to choose predetermine a significance level. We choose that to be 5%, which is the most commonly used significance level. We choose alpha to be 5%. The test statistic is minus of this t statistic. It is reasonable because when xn bar is much less than 500, which is evidence against the null hypothesis, the test statistic is large. And also, asymptotically, under the null hypothesis, t is asymptotically standard normal. So that is a good test statistic. And critical value we found, the right critical value is the standard normal critical value, Z alpha. So for our observed sample, we can figure out what T is. T is minus square root of 45 times minus 45 divided by 32, and that is approximately minus 9.8, I think, right? So we actually calculated this already at the beginning of last lecture. 9.4. So that's approximately 9.4 plus 9.4, because you got two minus signs here. And the critical value Z alpha for 5% is 1.645. You can look it up in the normal table. And that is 1.645. And clearly, T is bigger than the critical value. Therefore, we reject the null hypothesis. So what we should say verbally is that the battery runtime, the runtime of U500 appears to be significantly, statistically significantly, or we just say significantly, statistically significantly less than 500 minutes at significance level 5%. So that would be your verbal conclusion from your testing. So the runtime of the battery U500 is statistically significantly less than the 500 minutes claimed by the company at significance level 5%. Now, what if you do not want to predetermine a significance level? Suppose you do not want to commit to a 5% or 10%, what can you do? If you do not want to pre-commit to a significance level alpha, what you can do is to report a p-value, and that's a common practice as well. You can report a p-value. So in order to define the p-value, so how do you define the p-value? To do that, we first want to define the null distribution of the test statistic. So suppose the T, big T, denote your test statistic. We want to define a function G to be the CDF of T, assuming that the null hypothesis is true. So it's important in the definition that you're assuming the null hypothesis is true, because otherwise the CDF is not determined because we do not know the true parameter value. Under the null, we know the parameter value because the null is a simple null. So under the null, we know the true parameter value, we know the distribution of T, or maybe the asymptotic distribution of T, maybe not the exact, but the asymptotic distribution of T. We can define the CDF of T, and we use G to denote that CDF. Okay, so G is the CDF of the test statistic under the null hypothesis. So the p-value, on the other hand, is 1 minus G evaluated at T. The p-value is simple, it's just 1 minus G of T. T is your test statistic. So for any given sample, suppose that the realization of the test statistic is T star. So T star is the number you get after plugging in your numbers, the data, into the formula for the test statistic. So T star is the realization of T for your given sample. If that is the case, then the realized p-value will be 1 minus G of T star. That's a realization of the p-value, which is probability that T being greater than T star given H naught, right? Just by definition of G. And that is probability that the test statistic being greater than this realization given H naught. So we have learned that large values of the test statistic is evidence against the null hypothesis. So this probability can be interpreted as the probability that a random sample, any random sample, shows more evidence indicated by this greater than sign, more evidence than your given observed sample. So this is the probability that a random sample shows more evidence against the null than your current observed sample, assuming that H naught is true. So p-value is the probability of observing something that's more against the null than you already observed in the given sample. So if you think about this for a moment, you see if this p-value is very small for your current sample, that means your current sample is already very, very against the null. It's very unlikely for you to observe something that's more against the null than your current sample. So a small p-value means your current sample provides a lot of information against the null. On the other hand, a big p-value means your current sample doesn't provide a lot of evidence against the null. In fact, for the battery runtime example, we have already calculated the p-value at the beginning of the previous video. The informal calculation of the probability that Xn bar being less than 455, that was in fact the p-value. And we have already calculated that, and that is less than 0.001. So that's very small. So remember that is about 1 minus phi of 9.4, which is very small. So the p-value calculation for this example also provides very strong evidence against the null hypothesis that mu equals 500. In fact, you can use p-value for hypothesis testing as well. Using p-value for testing is in fact equivalent to using the test statistic that you use to define the p-value and the critical value. So what do I mean by that? You can, suppose you have the p-value, you can define a test, a hypothesis test with significance level alpha to be the indicator that the p-value is less than alpha. That is, if you observe a p-value that's less than alpha, then you reject the null. If you observe a p-value that's greater than or equal to alpha, you do not reject the null. That's a decision rule, and therefore, that's a decision rule determined by data, therefore it is a hypothesis test. And that is in fact equivalent to the test defined using the test statistic and the critical value. So why is that? To see why that is true, you should go back to the definition of the p-value. Definition of the p-value is that p-value is 1 minus g of t. So that's the definition of the p-value. And that gives us g of t being greater than 1 minus alpha. And in typical cases, g is strictly increasing and continuous. So that is 1 t being greater than g of inverse 1 minus alpha. So the test that you defined using p-value is the same as the test you defined using the test statistic. And this is the 1 minus alpha quantile of the null distribution of t, and that is the appropriate critical value to use when you use t as the test statistic. So that is the test. So that is so reporting the p-value, you really don't lose anything because the p-value can be translated into a hypothesis test. So it's a good idea to report a p-value when you are doing hypothesis testing. Now let's consider some examples. In these examples, we're going to go through the steps in which you translate a verbal description of a hypothesis testing problem into more formal hypothesis testing language. In this example, consider the banner ads the advertisement, the banner advertisement on the web page that you see whenever you go to any web page that's not ad-free. So this banner ads for this X Coffee on a national newspaper's website receive an average of 750 hits, 750 clicks each weekday morning. And you work on these ads for X Coffee. You created a new banner that is more annoying for the consumer. That's very hard to ignore. You have to kind of do something about the banner before you can look at the web page, for example. So you create a hard to ignore new banner that you believe will generate more hits for the advertisement. And now suppose you run the new ad for 60 mornings and find that the average hit is 768 with the standard deviation 68. Now, can you conclude that the new banner generates more hits than the old banner, which generates 750 hits on average? So what is the hypothesis? Clearly, the hypothesis that you want to give the benefit of doubt is the old number of hits. So hypothesis is mu equals 750, where mu is the expected number of hits on a weekday morning, and x is the number of hits on a random weekday morning. So that is your null hypothesis. And for alternative hypotheses, you want to think about what you actually want to prove here. You want to prove that the new banner improved upon the old banner. So therefore, your alternative should be mu being greater than 750. Now that's your null and alternative hypothesis. What do you want your test statistic to be? Now you have collected a sample with your sample x1 to xn from n mornings, where n is 60, and you have your sample average, and you have your sample standard deviation. How do you create your test statistic? Because you're testing about sample mean, it's reasonable to use the t-statistic to construct your test statistic based on the t-statistic, which is square root n x n bar minus 750 divided by the sample standard deviation. This is a reasonable test statistic to use because larger x n bar is evidence against the null and for the alternative. Okay, so larger values of t is evidence for the alternative. And also, under the null, when 750 is the true mu, this statistic has asymptotic distribution that's standard normal. So you know the null asymptotic distribution of the test statistic. So therefore, that's a very good test statistic. Satisfies the two requirements for test statistics. And now the third step is to determine that null distribution, G. The null distribution G, as I said, it is the standard normal. So G equals the probability that T is less than or equal to little x given mu equals 750. And given mu equals 750, the test statistic equals root n x n bar minus mu divided by sigma n hat, and that is asymptotically standard normal. So therefore, that is phi of x. So G is phi of x. And now try to find the p-value. P-value is simple. It's just 1 minus g, which is phi of x, and evaluate it at t. Then that is 1 minus phi square root n x n bar minus 750 divided by sigma n hat. And that is 1 minus phi square root of 60. X n bar is 768, I think, minus 750 divided by 68. And what is that number? Let me try to do this very quickly. That is about 2.05. And if you use the normal table that we provided before, you can look up this probability. And this probability turns out to be 1/2 minus 0.4783, and that's about 2.17%. So you calculated the p-value and you calculated the realization of the p-value. That turns out to be 2.17%. So now the last step is to verbally explain your result. This is very important. How do you explain your result verbally? This cannot be skipped. You can do two things. One is literal interpretation. Literally, what is this? Literally, this means the p-value is 2.17%, which is kind of small, which means the large sample two-sided t-test of significance level 2.17% or higher will reject the null hypothesis. Or if you are doing a large sample two-sided t-test of 5%, you reject the null hypothesis. And in more practical terms, you should say the improvement brought about by the new banner is statistically significant. So the improvement brought about by the new banneret is statistically significant at level 2.17% or higher. So these are the two ways to verbally explain your result. One more literal and one that's more understandable for common people. So that's one example. Let's consider another example where we do a two-sided test, which is really not all that different. So suppose in this example, workers at a software company have been working from home, WFH, which is a training term nowadays, have been working from home during the pandemic, and the management of the company wants to know whether working from home affects productivity. It could decrease or could increase productivity. Does it make any difference? So what the information they have is as follows. Pre-pandemic, when they were not working from home, a random worker writes 15 lines of code on average. So if X is the lines, the productivity measured by lines of code produced by the worker, then expected value of X pre-pandemic is 15 pre-pandemic. And you want to know whether post-pandemic, whether the productivity is higher or lower than this 15%. So you collect data, the management collect the data on 62 work from home workers, and they find an average productivity of 14.6 lines, which is slightly lower than 15, but with also a sample standard deviation of 3.8. Should the management conclude that the working from home affects productivity? So that's the question you want to answer. So to answer that question, you first want to write down your hypothesis. The null hypothesis is clear. You want to know the post-pandemic expectation is the same as before, or the during pandemic productivity is the same as before in expectation. And because the management only wants to know whether it makes any difference, so the alternative hypothesis should be the two-sided alternative. Now with the two-sided alternative, the test statistic T should be the absolute value of the T statistic. The reason is violating the null on both sides, being too large or too small, are both consistent with the alternative. So we want the test statistic to be large when the sample average is much lower or much higher than 15. So therefore, we want to use the absolute value to reflect that fact. Using the absolute value will help this test statistic to satisfy the first requirement. Large value of it reflect evidence for the alternative. And for the second requirement of the test statistic, this is also satisfied because asymptotically under the null, this is asymptotically standard normal, and the absolute value is asymptotically absolute value of the standard normal. So we know the null distribution of T. So the null distribution of T is the probability that T being less than or equal to little x given the null hypothesis, and that is the probability that standard normal absolute value being less than or equal to little x h naught. So for standard normal, absolute value being greater than or equal to little x means the standard normal is greater than or equal to x, or less than or equal to minus x. Or in other words, it's twice the probability that it's greater than or equal to little x. So therefore, that should be 2 times 1 minus CDF of standard normal at x. So Gx should be this. Now, using this information, we can write down the formula for the p-value. P-value should therefore be 1 minus 2 times 1 minus phi of x, phi of t. So therefore, that should be 2 times phi of t minus 1. And you can look this up from the normal table, and you found that in this example, once you plug in all the data, you found this p-value is in fact about 40%, 40.62%. So I will skip the details. You can figure it out at your spare time. So that's 40.62%. And that is not a very small p-value, that's quite large. So that's larger than the usual significance levels, 5%, 10%, or even 20%. So you can conclude that H naught is not rejected at commonly used significance levels. And therefore, working from home doesn't have a statistically significant impact on productivity at any commonly used significance levels. So that's how you might do a two-sided test in an example. One last thing about hypothesis test I want to mention is how to interpret non-rejection. So this is actually a word of caution for interpreting non-rejection. When the hypothesis rejects the null, then you can be quite confident that the null is not true. You can take the alternative as being true. But when the hypothesis test does not reject the null, can you take the null hypothesis as being true? Typically, that shouldn't be done. You shouldn't take the null hypothesis as being true when you do not reject the null. In fact, this is a very commonly made mistake. I want to show you something. This is regarding our current pandemic. At the beginning of the pandemic, the United States were very, very strangely against wearing masks. Look at, this is what the Surgeon General, US Surgeon General said on February 29. That's the beginning of the pandemic for the United States. In this Twitter feed, he says, they are not effective in preventing general public from catching the coronavirus. So the Surgeon General says masks are not effective in preventing general public from catching coronavirus. That's against most people's common sense. And after a while, after several months, the scientific community found more and more evidence for masks to be effective. But even then, there are still people in June, for example, who are claiming masks don't work. And in August, people are still claiming still no conclusive evidence justifying mandatory masks. So what are they doing? They are making one simple mistake. That is, they are interpreting a non-rejection as the null being true. So they're equating non-rejection to the null hypothesis being true. And that is a very wrong way to interpret a non-rejection. Non-rejection can happen often, can be and often is a result of a lousy data or no data at all. If you have no data at all, you're not going to be able to reject the null, but that's not evidence for the null. That's just no evidence for the alternative. Let's consider like a numerical example to show you how misleading equating non-rejection to a true null can be. So suppose that your variable of interest is a normal follows a normal distribution with an unknown mean mu and a known variance 25. You want to test whether mu equals 0 or not. Say mu is the efficacy of a mask, the protection that a mask provides for you. And the null hypothesis is that it doesn't provide any protection, mu equals 0. And H1 is that it does provide protection, mu is greater than 0. Say at the beginning of the pandemic, you really don't have very good data. Suppose you only have a random sample from 25 people doing something like being actively exposed to the virus or something. So you have n equals 25. And to test this hypothesis using the data set that you have, you can consider this t statistic. That's root n xn bar minus 0 divided by the standard deviation 5. And for this, it's easy to figure out what the right critical value should be. The critical value should be the z-score, the one-sided standard normal critical value, z alpha. This test has the right null rejection probability. The probability of type 1 error is alpha, is exactly alpha. But now, let's see what is the probability that it rejects when the null is not true. Let's say when the null hypothesis is 0.5, sorry, when the true mean is 0.5, it is in the alternative, not in the null. The null doesn't hold. The null doesn't hold. Does the test then reject the null? We can calculate that probability. The probability that it rejects the null under this alternative value is probability that t is greater than z alpha. And t in this case equals root n, which is 5, times xn bar minus 0 divided by 5. So 5 and 5 cancel out. So the test statistic is actually equals to xn bar in this simplified example. So probability of rejection is the probability that xn bar being greater than z alpha. But under the alternative that mu equals 0.5, t is not standard normal, but instead xn bar minus mu is standard normal. So xn bar minus mu is root n xn bar minus mu divided by the standard deviation 5, and that is exactly standard normal. But because mu is 0.5, xn bar minus mu minus 0.5 is standard normal. So probability that xn bar being greater than z alpha equals xn bar minus mu greater than z alpha minus 0.5. So that's given mu equals 0.5. And xn bar minus mu is standard normal. So therefore, this probability equals probability that standard normal being greater than z alpha minus 0.5. Suppose that alpha is 5%, then z alpha is 1.645. This probability will be probability of standard normal being greater than 1.145. That probability turns out to be 12.51%. That is a very small probability, relatively speaking. It's bigger than 5%, but it's still very small. There is a 87.49% probability the test that's based on t being greater than z alpha does not reject. So it's very high probability the test does not reject the null. Can you take that as evidence for H null being true? Clearly not, because H naught is not true in this case. So it is So therefore, it is wrong to interpret a non-rejection as a true null, as the true being, as the null hypothesis being true. And this simple mistake, a lot of people believe, cost America a lot of lives. So don't make this mistake.